Hi, thanks for joining me. Today I'm going to be going over a STEP problem. So STEP is the entrance exam you have to do if you want to study undergraduate mathematics at the University of Cambridge, and I believe now quite a few universities across the UK require STEP to get a place at that university. So STEP is the other place, so for Cambridge I'm from Oxford, so there's a bit of a rivalry there, but I thought it's still a really fun paper to do, very challenging, and you sort of sit it in your final year of high school in the UK, so when you're in year 13, which is around when you're 18 years old, just before uni, and it kind of decides whether or not you get your place at Cambridge. So it's a very stressful exam. Anyway, it's usually held in June, sort of July, so I thought I'd make a few videos where I go over some STEP problems. So if you have any specific STEP problems which you'd like me to go over, let me know in the comments down below, and I'll leave a link and stuff to the official Cambridge STEP website so you can find more information about the STEP paper and stuff if you're interested. Anyway, I'm waffling now. Let me get stuck into the problem. This comes from Step 3 from 2020, and this is problem 1. So it's a crazy looking integral problem. Okay, so we have for a and b non-negative integers, so either positive integers or 0. We're defining this function here, IAB, to be the integral from 0 to pi over 2 of cosine of x raised to the power of a times cosine of bx dx. Okay, and this problem is split into two parts, 1 and 2. Part 1, we want to show that for all a and b positive integers, so a and b are not 0, just be careful there, positive integers, we want to show that I of ab is equal to a over a plus b times I of a minus 1 times b minus 1. And I guess you can see why we don't want a and b to be 0, because then we have I of one of these things here would be negative 1, but we haven't defined I for negative numbers. Okay, so that's why we have a and b positive integers. And then part 2 is we have this even crazier looking expression. We want to prove now for n and m non-negative integers, so we're including 0 here, the integral from 0 to pi over 2 of cosine x to the power of n times cosine of n plus 2m plus 1 x dx is equal to this horrible looking expression on the right hand side, minus 1 to the power of m times 2 to the n times n factorial times 2m factorial times n plus m factorial, all divided by m factorial times 2n plus 2m plus 1 factorial. So a lot of factorials, n's and m's floating about everywhere. So yeah, if you want to have a go at this problem, pause the video now and give it a go for yourself. One thing I will say is this is a very classic STEP problem where they give you a family of integrals sort of indexed by the natural numbers, or in this case, two sets of the natural numbers, and you've got to sort of find relations between them. Anyway, if you want to have a go, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so let's get into the solution for part 1. As I said, this is a very sort of stereotypical STEP problem where they give you a family of integrals and you want to define one in terms of perhaps the next one down. So that's what we're doing here. But the way we do that, and the way you always do that, is integration by parts. But we've got to sort of work out what thing we want to differentiate and what thing we want to integrate. But remember, we want to write this thing here in terms of I of a minus 1, b minus 1. But in particular, we've got that a minus 1 here. And we can see here, if we differentiate cosine to the a of x, we're going to drop down an a and bring an a minus 1 into the exponent. So that suggests we should differentiate this thing here. So we're going to write u equals cosine to the a of x, and then the derivative of that du is equal to a times cosine to the a minus 1 of x. Then by the chain rule, we've got to multiply by the derivative of cosine of x, which is minus sine of x, like so, and then a dx. Okay, and we have to integrate the other thing, so that's cosine of bx dx. Okay, and I guess remember this is part 1, and remember it says that we can assume that a and b are positive integers. So that tells us that this thing here is 1 over b times sine bx. Of course, if b was equal to 0, v equals this thing here, because obviously if b was equal to 0, then this guy here would be identically 1, but we don't have to worry about that because a and b are positive. So we get this thing here. So just plugging this into here, we get that IAB is equal to UV, which is 1 over b sine bx times cosine to the a of x, and that's between pi over 2 and 0, and then minus the integral of v du, but obviously the minus is going to cancel with that minus sign here, and we can bring the a and the 1 over b out, so we get plus a over b times the integral from 0 to pi over 2 of cosine to the a minus 1 of x, times sine bx times sine x. just write it here, like so. Okay, now this thing here evaluates out to 0, which is quite nice. Let's just check that. When we plug in x equals pi over 2, cosine of pi over 2 is 0, and because a is a positive integer, we got 0 to the power of a positive integer. So this thing is 0, so this whole expression here is 0, great. And when we plug in x equals 0, we got sine of b times 0, which is 0. So 0 minus 0, this thing vanishes. The only thing we need to worry about is this integral here, so it's the integral, or a over b, times the integral from 0 to pi over 2 of cosine to the a minus 1 of x times sine x times sine bx dx. Okay, let me clear up the whiteboard and we'll continue. Okay, so we've just shown that for a and b positive, IAB is equal to a over b times this integral here. And now we've got this cosine to the a minus 1x here, which is great, but we want to write this thing here in terms of cosine b minus 1x, so it's quite clear that we're going to have to use our double angle formulae. So cosine, let's just recall cosine of, let's write bx minus x is just equal to cosine of bx times cosine of x plus a sine of bx times sine of x. Okay, so this sine bx x term here, we can write in terms of cosine of this thing here is just b minus 1 times x, like so, and this thing here, cos bx cos x. So let's just rewrite this thing here. So it's equal to a over b times the integral from 0 to pi over 2. This cosine a minus 1 x term stays the same. And now sine x sine bx is just equal to cosine of b minus 1x, then minus cosine x cosine of bx, and then dx, just like so. Okay, and now we're just going to split this into two integrals. Keep this a over b out front, and then we get the integral from 0 to pi over 2 of cosine a minus 1x times cosine b minus 1x. Now cosine of b minus 1x dx, like so, and then minus this guy, the integral of this guy times this guy. But if we bring this cosine a minus 1x times this cosine x together, we get cosine to the ax. This is minus the integral from 0 to pi over 2 of cosine to the ax, and then we've got this cosine bx here as well, like so. Okay, perfect. But now we notice this guy here is cosine to the a minus 1 of x times cosine b minus 1x, which is precisely I of a minus 1 b minus 1. So this thing here is I a minus 1 b minus 1. And this thing here is minus this guy here, which is the integral from 0 to pi over 2 of cosine to the ax times cosine of bx dx, which is precisely I of ab, like so. And of course we've still got this a over b out front, and this thing all equals I of ab. So we've got IAB equals a over b times I of a minus 1 b minus 1 minus this IAB, bringing this IAB onto the left hand side and rearranging and cancelling some b's in the denominator, you're going to get the required result, i.e. I of AB is equal to a over a plus b times I of a minus 1 b minus 1. I would write it out, but there's no space. Anyway, let's move on to part 2. Okay, so for part 2, what we want to do is show this crazy integral equals this crazy expression on the right hand side. And as with pretty much all of the set problems I've seen like this, you have to use induction. So you use the result from part 1, that sort of recurrence relation we got, to show this guy here is true using induction. But here we've got to be a bit careful because we've got two variables, n and m. Now in the problem it said use induction on n, but yeah, that's what you'd try anyway, try and do induction on one variable by fixing one. So we're going to fix m. So we're going to fix m to be just some non-negative integer. Doesn't matter what it is, we're going to fix it. And we're going to let m, we're going to proceed by induction on n. So we're going to look at the base case when n equals 0 first. So the base case, this is when n equals 0. So on this left-hand side, what do we have? It's just the integral from 0 to pi over 2. Cosine to the nx is just 1, because n is 0, so we've got cosine of x raised to the power of 0, so that's just 1. Then this guy here is, obviously n is 0, so this is just cosine of 2m plus 1 x dx. Now remember, m is non-negative, so 2m plus 1 is strictly positive, so this guy here is never 0. So we can write this then as 1 over 2m plus 1 times sine of 2m plus 1 of x, and that's between x equals pi over 2 and 0. Now clearly when we plug in x equals 0, we're going to get 2m plus 1 times 0, which is 0, and sine of 0 is 0, so that vanishes. So we only need to worry about when x is pi over 2. So this is just 1 over 2m plus 1 times sine of 2m plus 1 over 2 times pi. Okay, actually I'll write this as 2m plus 1 times pi over 2. Okay, so we've got an odd number times pi over 2. And now if we just look at a sine graph, like so, it looks something like that. Here we've got pi over 2. And here we've got 3 pi over 2. The next one will be 5 pi over 2, which will be somewhere here. Okay, and the next one will be 7 pi over 2 and so on. So we see that the odd multiples of pi over 2 are either going to be 1 or minus 1. And to work out which one they are, we can sort of see there's a pattern that the ones which are where the numerator is strictly 1 more than a multiple of 4, so pi over 2 or 5 pi over 2 or 9 pi over 2 or whatever, those are always going to evaluate out to be 1, and the ones which are sort of 1 less than a multiple of 4, so 3 pi over 2 or 7 pi over 2 and so on, those are going to evaluate out to minus 1. So if we look back at this guy here, when m is even, we see that this guy here is 2 times an even number plus 1. So 2 times an even number is a multiple of 4, and then that guy plus 1 is obviously 1 more than a multiple of 4. So when m is even, this guy here is going to equal 1. And when m is odd, you can check for yourself. If m is odd, then you can write m as 2k plus 1. So then this would equal 4k plus 2 plus 1, which is 4k plus 3, which is 1 less than a multiple of 3. So we've got an odd multiple of pi over 2, where the odd number sort of in front of the pi over 2 is 1 less than a multiple of 4. So this thing here is going to evaluate out to minus 1. So that was a lot of waffling. Basically, if m is even, this guy here equals 1, and if m is odd, it equals minus 1. And a nice way of representing that is just minus 1 to the power of m. So I just kind of wanted to go into detail about that if you've not seen that before. But this thing here is just minus 1 to the power of m, for m being a positive integer. And this thing here is, or non-negative integer, so this thing here is just minus 1 to the m all over 2m plus 1. Okay, so in the case n equals 0, our left-hand side equals this thing here. What about our right-hand side? Well, that equals, just plug in n equals 0, we're going to get a 2 to the 0, which is 1, n factorial is 0 factorial, which is 1, and we're going to get a 0 plus m factorial, which is m factorial, and on the bottom we're going to get a 2 times 0 plus 2m plus 1 factorial, which is of course 2m plus 1 factorial. So I'm just going to ignore all the 1s, so this is just minus 1 to the m, times 1 times 1 times 2m factorial, let me just rub this bit off, times 2m factorial, times an m factorial, and that's divided by an m factorial times a 2m plus 1 factorial. Of course these m factorials will cancel, and now I'm left with this minus 1 to the m times 2m factorial over 2m plus 1 factorial, but of course that thing there is just 1 over 2m plus 1, so we get that this thing here is minus 1 to the m divided by 2m plus 1, which is exactly the same as that guy there. Okay, so that was a long-winded way of proving the base case. Now let's use prove by induction and then complete the proof. Okay, so we've done the base case, let's continue. We're going to assume that this thing holds, this is valid for some n in the natural numbers or 0, and then we're going to look at n plus 1. So what happens when we plug in n plus 1 into this expression here? Well, notice when we plug in n plus 1, we're going to get something in terms of that I function we had earlier. When we plug in n plus 1, we get precisely I of n plus 1, because this thing here will turn into an n plus 1. And then when we plug in n plus 1 into this guy here, we're going to get an n plus 1 plus 2m plus 1, which is going to be n plus 2m plus 2. So n plus 2m plus 2. Now remember, n and m are non-negative integers, so n plus 1 is strictly positive, and this guy here is also strictly positive, and they're both integers. So that means we can use the result we showed in part 1, sort of reducing this down by 1. So remember, we get that this I of ab is equal to a over a plus b times I of a minus 1, comma b minus 1. So we can write then this is equal to, well, the a, which is just n plus 1, all over n plus 1 plus n plus 2m plus 2, which of course is just 2n plus 2m plus 3, and that's I of n plus 2m plus 1. But this guy here is precisely this guy here. Okay, so I of n, when we plug in a equals n, we get that thing there. And when we plug in b equals n plus 2n plus 1, we get that guy there. And by assumption, we're assuming that this integral here equals that integral there. So let's just plug it, sorry, not the integral, the expression on the right-hand side. So let's just plug that in. This is equal to now n plus 1 all over 2n plus 2m plus 3 times this ugly-looking thing here, minus 1 to the m, times 2 to the n, times n factorial, times 2m factorial, times n plus m factorial, all divided by m factorial times 2n plus 2m plus 1 factorial. So this sort of, we made this expression even uglier. Now what we want to do is sort of have a bit of an algebraic play around with this expression here and show that this guy here equals essentially this thing here, except with n replaced with n plus 1. Okay, so we're going to keep some terms to the one side, so we're going to keep this minus 1 to the m like that. This 2m factorial we're going to keep here, and then this m factorial we're going to keep on the bottom. And notice this n plus 1 times n factorial is going to give us an n plus 1 factorial, like so. And what do we have left? Well, we have 2 to the n times n plus m factorial divided by this guy here, which is 2n plus 2m plus 3, times this 2n plus 2m plus 1 factorial, like so. Okay, so we've got this thing here, which is fine, and we just got to sort of have a play about with this thing here. And we want to get this 2 to the n turning into a 2 to the n plus 1, and we want to get this n plus m factorial turning into an n plus 1 plus m factorial, and we want to get this thing on the bottom to be 2n plus 2m plus 3 factorial, because you're going to see when we plug in n equals n plus 1 into this thing, we get 2n plus 2 plus 2m plus 1, which is 2n plus 2m plus 3. I apologise if the n's and m's I'm saying sound the same. I'm speaking very quickly. Anyway, so we have this thing here. So we want to get the bottom to look like 2n plus 2m plus 3 factorial. Well, we almost have that, but we're just missing a 2n plus 2m plus 2. So let's just multiply the top and bottom by 2n plus 2m plus 2. So then on the bottom, we're actually going to get 2n plus 2m plus 3 factorial. So that's going to get rid of this thing here and put a factorial here. And then we've got here now 2n plus 2m plus 2. Of course, we can factor out a 2 from here and plonk it on this 2 to the n here, which is going to put one more into the exponent, so n plus 1. And then that gives us here n plus m plus 1, like so. But of course, combining the n plus m plus 1 and the n plus m factorial is going to give us an n plus m plus 1 factorial, like so. Like so. Okay, so we've shown that I of the sort of, we assume that this holds for some fixed n, and we're sort of doing the inductive step, and we've shown that this guy equals this thing here. And if you just check for yourself, this thing here is the exact same thing as this thing here, except with n replaced with n plus 1. You've got this minus 1 to the n, that stays the same. This 2 to the n is 2 to the n plus 1. This n factorial is this n plus 1 factorial. This 2m factorial is this 2m factorial. N plus m factorial is now n plus 1 plus m factorial. The m factorial on the bottom is still there, and the 2n plus 2m plus 1 factorial is 2n plus 2m plus 3 factorial. Okay, so that we've shown that the inductive step sort of holds, and that concludes the proof of part 2. I hope you have enjoyed this video. I thought this problem was quite fun. When you first look at the integral of from 0 to pi over 2 of cosine to the a minus 1x times cosine bx, it kind of seems like it's something you won't be able to evaluate, but in fact you can using this trick. But yeah, I hope you have enjoyed this video. Do let me know if you have any specific step problem requests that you want to see. And if you are new here and you've enjoyed this video, please do consider subscribing and checking out some of my other fun maths videos as well. Anyway, I'm going to stop waffling. Thanks for watching. I'll catch you in the next one. Have a great day.